All right. Let's see. Okay, you should see the presentation now. Let's start from where we left off. So we are looking at side effects, um, and we were looking at how to reason about programs that use side effects, right? In particular, we saw this idea of aliases, and we also introduced the concept of physical and structural equality. And we saw an example how to interpret what happens when you ask questions about physical and structural equality, right? So the other thing that happens when you add side effects to a language is that type system gets a little bit complicated in unusual ways, right? So one of the ways it gets complicated is this idea of value restriction. So this concept has a name, but let's keep that aside for the moment. Let's just look at a very simple example that motivates why what happens when we add side effects to OCaml, right? So we have a purely functional language, we add side effects, something interesting happens. Consider this program, right? This program is very simple. So it says let R equals an empty list, okay? And then it says, oh, create an alias for R, which is an int list, right? And then R1 is an int list. Actually, R happens to be an empty list, so that's fine. And create a R2 such that R2 is a string list. So I'm explicitly ascribing types here, right? So you don't need these types. I'm using these types for a particular reason, right? I'm saying R2 is string list, and it has the same value as R. So these are just values, right? So the value of that is going to be an empty list. So that is also fine. And then I say, okay, return a pair of R1, R2. So both of these are empty lists, right? So the value is empty list, but because we had explicitly ascribed the types here, the pair will have the type int list star string list, right? Int list star string list. So the only thing that is interesting here is R has type alpha list, right? Because it's an empty list. Empty list constructor is the same constructor for arbitrary list contents, right? So R itself has type alpha list, but otherwise nothing is surprising here. You've seen this example previously, and nothing is going on here. So let's modify this example in a simple way, right? So let's just do, actually, let me clear all the executed output so that I don't give away the surprise. Restart and clear output. Restart and clear outputs. Okay, so now we had this example. Yeah, so we saw this example. I'm going to modify this example in a very small way. I'm going to say instead of an empty list, I'm going to make R a reference to an empty list. So I create a ref cell that points to an empty list, okay? And then correspondingly, I'm going to change the type of R1 and R2 such that they are now int list ref and string list ref, right? Observe that this is int list and string list here, but here, because I'm adding a reference to a list here, so this becomes int list ref and string list ref. And I simply return the pair of R1 and R2 now. If you run this program, right, we get an error, right? So we get a compiler error that says on line 3, right, this line, R happens to be an int list ref, right? But an expression that is expected of type string list ref, because I say R2 is a string list ref. So the right hand side expression must be a string list ref. But what I have here is an int list ref, right? Type int is not compatible with type string. So the question you have to ask is, okay, why is this program showing an error, but a similar program here is not raising an error, right? The only thing that I've done is I've added a ref here, and I've changed the types correspondingly to add refs, right? Why is the compiler complaining? Right? Yeah, Sarthak has the right answer. So is this because each cell can hold only? Yeah, that's exactly right. Um, it is because each cell can only hold one type of value, and in order to see what can happen, right, it is better to ask the question of what happens if you allow the cell to hold different sorts of values, right? If this program were allowed, what can go wrong? So here is so let's first look at how OCaml is sort of catching this error, right? So OCaml has this idea of value restriction, right? And if you look at the type of ref of empty list, right? So the thing that you see here is it's not an alpha list anymore. It is this thing known as quote underscore weak, right? And so what this says at a high level is that this particular R is only weakly polymorphic. What does weak polymorphism mean? Weak can be unified with exactly one type. So you can unify, if you unify it with say integer, that particular type gets specialized to integer. You cannot unify that with a string later, right? I wouldn't go too deep into what weak polymorphism is, but I'm just going to give you examples and try to explain what is going on. That is the concept, right? That's the high level concept. You can have something weakly polymorphic. It can get unified with one particular concrete type, and that's it, right? You don't have the usual polymorphism which says if I have an alpha list, I can use it in a string list and an int list place. Right? But why does this value restriction exist? Right? So this is the example. Let's say we just take the same first three lines, right? I'm writing this in the slide as a markdown and not a cell because this wouldn't compile, right? If you run this code in OCaml, this wouldn't compile. I want to make a point here, right? So let's say R is a reference to an empty list, and I say R1 is a same alias, right? It's an alias to the reference to an empty list. I ascribe the type int list ref, and similarly R2 is an alias. I give it the type string list ref. Now, because R1 is an integer list reference, I can store in it an integer list, right? Because it's a reference to an integer list, I can store an integer list into it. I'm going to take the singleton list 1 and I'm going to store it into R1, right? Now, R2 and R1 are aliases of the same underlying ref cell, right? So, because R2 is a reference to a string list, I can dereference R2, right? I dereference R2. Oops. What happens what do I get when I dereference R2? Because R2 is a string list reference, I will get a string list, right? I'm going to get the head of the list, right? So the list head should be a string, and I'm going to print endline the string. So you can see what is going on wrong here, right? If I'm able to do this, I will get an integer. I won't get a string. So at this point, the thing that I will get out will be an integer, not a string, because R1 and R2 are aliases of the same thing. And this breaks type safety, right? So we are storing in an int list in R1 and reading it out as string list through R2, and this is bad. And so that's the reason why we have value restriction in the first place. It turns out that value restriction was actually something that the original designers of a language, a precursor to OCaml called standard ML, did not come up with in the original standard. So they formalized, they initially implemented the language, they added references, and the first version of the language had this bug. So they had to go and fix the specification such that they added value restriction into the language. So this is not something that, it seems so obvious when I explain it to you, but for the initial designers of the language, they didn't think about this case. And it is not surprising, right? So we don't always design languages with full proofs of correctness all the time. So Java, initial version of Java also got a concept called subtyping wrong. Because it got the concept called subtyping wrong, Java, unlike OCaml, which can erase all of the types, we saw type erasure earlier, right? So unlike OCaml, which can erase all the types, Java has must do dynamic type checking for array typecasting. Details are not important here, but the point is language designers do get the designs wrong, and you have to sort of live with it forever. In the case of Java, but in the case of standard ML and OCaml, we sort of knew um, how to not live with it and actually fix it and break code that uses that feature. Anyway, so if this feature were allowed, it breaks type safety. This code will segfault, right? If I run it in OCaml, if this code type checks. So this concept called value restriction exists. Um, in OCaml, value restriction is implemented as a syntactic check of what expressions are allowed on the right hand side, right? What expressions are allowed on the right hand side, right? If the expression on the right hand side is belongs to a particular class, right? I won't define what the class is. The details are not important here. Then the variable that is on the left-hand side of the expression gets a weakly polymorphic type. So because this is weakly polymorphic, and you first unify it with the int list reference, right? The type gets unified to an int list reference. And here, because this is a different type here, which is a string list reference, int is not compatible with string. Details are beyond the scope of this course. It's not important, but it is important to know that the concept called value restriction exists. And here is an example of what can go wrong if value restriction did not exist. Okay, so how is value restriction relevant to you, right? So when you write programs in OCaml, you can do partial application, right? So since value restriction is implemented as a syntactic check, it is not precise, right? There are examples where something is okay to be fully polymorphic, but because of the way value restriction is implemented, which is an approximate way of saying it's conservative, right? So it looks at the right hand side expression. It just says, okay, this fits to this class of things which I don't know, which might go wrong. So I'm going to give it a weakly polymorphic type. So here is an example that shows up in practice, right? When you do partial application. So here is an example. So I defined this function called swap list, right? What it does is it takes a list of pairs, right? Pairs of values, and for each element in the pair, it swaps it, right? When you have the pair AB, swapping is BA, right? For each of the elements in the pair and returns a new list. And the way I implement it is through partial application of map. So I want to do a map over each element in the list. And for each of the elements, I'm going to take A comma B and I'm going to return B comma A, right? So this is a partial application of a map where you only provide the higher order function, right? And if you happen to apply swap list with the list L, then what you end up getting is the swap list, right? But if you look at the type of this, it is a weakly polymorphic type because function application this way in lead binding happens to be one of the patterns where OCaml says there can be arbitrary effects here, so I'm going to make it weakly polymorphic, right? So that's the idea. So what is the so let's look at the type, right? The type seems okay, right? It takes a polymorphic thing week 2, a polymorphic thing week 3, a list of those things, and returns a week 3, week 2 list, right? But it so happens that these are weakly polymorphic. The problem is that if you use this in a context, the swap list, in a context where you apply it on 2 different types. So here is an example. So I apply swap list first on a singleton list with integer 1 and string hello. So the result I would expect is a singleton list again, where you have a hello and 1, right? And I again apply swap list on 1 comma 1, which is integer. So you get 1 1. You should get 1 1 out. But if you run this program, if you compile this program, OCaml will complain because swap list is weakly polymorphic. The first application here, right, forces unifies the types with integer and string. This becomes int string list and string int list, right? And because this is weakly polymorphic, this gets unified. So here it is expected that the type here is an integer, the type here is a string, just like the previous application, right? And that's not true. And here we have an integer. So OCaml complains this expression as type n, but an expression is expected of type string, right? So this is what you'll get. But there is an easy fix for this, right? If you happen to encounter value restriction, so weak polymorphism, when you apply partial application, you can just do eta expansion. So recall that eta reduction takes an expression which is lambda x, mx, and then reduces that to m. So eta expansion goes the other way, right? If you give some arbitrary lambda term, eta expansion just says add a lambda to the front, lambda x, and then apply that x, right? So here is an eta expanded version of the original expression. So what do I mean by eta expansion? I just take L as an argument here, right? And I apply L. So the original definition happened to be a partial application, right? I did not take an L. I did not apply an L. I was using the idea of partial application. Here, I'm not doing partial application. I define a function that takes one argument, and here it's fully applied, right? List.map, the higher order function, and list. This happens to be an expression. It's not a let binding of a variable, but a function. So this weak polymorphism does not kick in, right? And you get a fully polymorphic type that you would expect, which is alpha beta list and beta alpha list. And now this example works. So it is the takeaway from this section is it is not important to know what all expressions will trigger weak polymorphism, but if you encounter weak polymorphism while programming in partial application, you just eta expand it. You add the additional binder, right? You define it as a function. It will go away. Right? So that's the trick to get across weakly polymorphism. Okay, so that is weakly polymorphic, weak polymorphism in OCaml. So far what we've seen, we have introduced references, right? And all of the discussion has been about references. So references are one way to introduce mutable features in OCaml. OCaml also has this concept of mutable record fields, right? So you can think of mutable record fields as how you would operate on a structure in C, right? So there is going to be syntax and semantics. We'll first, okay. So there is a question in the chat. I'm going to try to answer that. Why is partial application considered to be weakly type? Without going into details, right? The expression on the right hand side is a function application, right? And here I'm defining a variable, right? This is some term. It's just a binder. It's not a function definition. It's just a binder, and I'm doing a function application here. So the high level idea is that when you do function application, there can be arbitrary effects internally, which might end up doing something similar to this one internally, right? Because OCaml cannot, when you do type checking, right, you don't actually go and look at the definition of the function. You just look at what those types are and try to apply, right? So OCaml is sort of assuming that there are arbitrary effects which it cannot reason about when you do this let definition, when you define this variable. But here you're defining a function, right? And this is not, because you're defining a function, that does not apply. Actually, there is a, there isn't a precise definition of when to do value restriction in OCaml or standard ML. So both of the languages are ML-like languages which take lambda calculus, right? And add mutations on top. So these are approximate, right? So it's hard to give a precise definition of why it should be considered. So I'm not going to give details because that goes beyond the scope of the course. You don't need to understand the details, is what I would say. But if you're interested, you should just check for, you should search for a paper called relaxed value restriction in OCaml. I think that defines the original value restriction and how OCaml does value restriction in a relaxed fashion. It actually allows weak polymorphs. So I'll just refer you to that paper. Okay. So let's move on. Okay, so mutable record fields. So there is going to be syntax and semantics, right? So for syntax, when you define records, we've seen records earlier. In records, all you define is a label and a type. You can make fields mutable in a record by just adding this mutable keyword to the front. Okay, and in particular, references in OCaml are actually just a syntactic sugar over mutable record fields. They actually have the same representation internally. So whenever we define this type alpha ref, what we are actually defining is a record, right, with a single field called contents, whose type is alpha, right, and it's a mutable record field. So you can change the contents of this record. Right? So that's the idea here. This is exactly how references are defined in OCaml. So references are not, even though we saw references as a primitive thing earlier, references are in turn implemented with mutable record fields. Okay, and yeah, you can just create a record just like we used to earlier. So here is a ref function that we saw earlier, which given an initial value creates a record with contents set to that value. So you just create a record, right, where you say contents equals X, right, that creates a record. And dereferencing, like getting the value is the same as the record syntax, right? So when I dereference a reference, all I do is I use the dot syntax. So the record dot contents, which is the label for the field. And the additional thing that we have on top of records is this way to update the context. So assignment, right, of a reference to a new value is done like this. So you take the record dot contents, right, left arrow, like less than minus new val. So this is sort of a syntax that we use for assignment to records. So that's all we have for records, right? And yeah, okay. So let's look at how we use it with an actual example. So the point is you can do, so OCaml is a functional programming language, but you can write, because of all of these beautiful features, right? You can write programs that you would naturally write in, say, C. So we are going to look at a program for writing doubly linked list. So this might seem strange, right? Oh, you have this functional language. We've been saying how functional programming is so great and so on. But why would you want a doubly linked list, right? Doubly linked list has a particular nice property, right? You can just, if you have a reference to some element in the list which you need to delete, you can delete that in constant time. So this is not true with the list definition that we've seen so far, right? Because the list definition is defined like an onion, right? So you have the head and a tail, head and a tail, head and a tail. If you want to delete one element in the middle, it is linear time, right? So you have to go all the way, take the tail of the list for where the head is the element that you want to delete, and you have to reconstruct the rest of the prefix of the list, right? So this is both time inefficient and memory inefficient. Of course, you want to do efficient data structures, right? You want to do circular linked lists and yeah, doubly linked lists and sequences and ropes and all of these fancy data structures behave much better than just purely functional ones. So hence in OCaml we don't particularly look down upon imperative programming, right? We sort of provide enough features for imperative programming such that you can get your job done, right? This sort of is a nice balance, right? If you look at Haskell, for example, that exposes pure functional programming, which has its benefits. I mean, it's not like you can't get the performance that you need, but you have to try a little harder. So a lot of the knowledge that we built based on mutable data structures, you have to sort of reimagine and then be clever to implement that. But in OCaml, you can just do it directly. And the history of why it is this way is unlike Haskell, which came from academic tradition. OCaml also came from academic tradition. Haskell is a playground for experimenting with new language features, right? So Haskell has this motto, which says avoid success at all costs, right? So this is very funny, but this is very true. Haskell is sort of always forward looking, it is less strict about having advanced features into the language, merged into the language. So Haskell happens to be the core language is simple, but contains so many advanced features. It's just a playground. It's a beautiful playground for exploring high-level ideas. Of course, it has its benefits, but OCaml has always been a language for getting things done, right? It is targeted at engineers in particular. So you want to write large software. Functional programming has its benefits. So let's develop a language which sort of appeals to people who might not go for functional programming in the first go, right? So that's the sort of place where OCaml is targeted at. And in particular, OCaml, initial versions of OCaml, right, try to be as close to Fortran programs, right? So people are writing Fortran, and then so the OCaml developers said, okay, we would like those programmers to use better abstractions, but we don't want them to give up all of their knowledge, right? They know how to write good Fortran programs. How can we take that and transplant it into a better setting? So that is why we have all these beautiful features in OCaml. So that's a bit of history. So with that, we can look at how we implement doubly linked list. Okay, so we define a node in a linked list with usual things, right? We have a value which is alpha. The node is also typed. So the type we define here is alpha node. It has a value that is alpha. It refers to, it has the next and the previous pointers. So the next pointer is alpha node option, right? It can either be there or not. And the previous is also alpha node option. And these are mutable, right? You can change the next and previous. Okay, so that's the definition of node. And typically for a doubly linked list, if you implement it in C, the head will be just a pointer to a node, right? And an empty list will be represented by a null. We don't have null here, right? We have to use some different type. So the type that we define here is alpha DL list, a doubly linked list, is a reference to a option node, right? So it's a reference, so it can be mutated, right? And it's an option so that you can represent the fact that an empty list is just a reference to a none option. So empty list is ref none, and non-empty list will have some node, right? And some node can have a previous and next and so on. Okay, so that's the difference, right? So because we don't want to use null, we have a separate type for doubly linked list and node. Node is precisely the same as what you would have in C, and here we have a different type, just so that we can get across this idea of avoiding the use of nulls. Okay, so how do we create an empty linked list? An empty linked list is just ref none. It's a reference to none, right? And yeah, if you want to get the first node, take the list T and then dereference it. So that can be So what does it give? It gives you an option, right? It is either none or some node. Actually, we can run this. Oops, I need to run this. We can run this to look at the type. So first, takes a doubly linked list and gives you a node option. So if it is none, you know that the list is empty. If it is some node, then the list is non-empty. So in order to check if the list is empty, we dereference that P reference, right? And if it is none, then the list is empty, right? So is empty is alpha DL list to Boolean, right? It is true or false. And we define helper functions to just fetch the value, the next and previous. So we just use dot. Right? The syntax highlighting is a bit off here. It should be black, but its value is sort of one keyword that you can use in OCaml, but it's not. It is also allowed for variable names, so that's why it's green. But otherwise, it should be black, right? This should be black. So given a node, you can get the value, right? Alpha node to alpha. You can get the next and the previous, right? And these are optional values. They are optional values because next and the previous may not exist. So we use options. Okay. So let's look at a few functions. These functions are going to look exactly the same as what you do in terms of logic, right? Exactly the same as what you do in C. Except that we have these minor differences, right? We don't check for null. We actually do a pattern match and things like that. So we are going to implement this insert first function. So what does this do? It takes a list and a value and inserts a new node. It creates a new node whose value is the given value, right? And it inserts the new node as the first node in the list, right? So if you have a list and you give it a value, insert first creates a new node which has the value, and then insert it at the first position, and it returns the node, newly created node, right? So what do? So we take the list, right, and the value. We first create a new node, right? A new node is created as saying, because it's going to be the first node, the previous is none, right? The next one is whatever the current first of the list is, right? And the value is v. So we've created the node here, n, right? And if t is empty list, so if the list is empty, then we are not doing anything here. But if the list is non-empty, right? If the list is non-empty, there is an old first, right? And because we are inserting the new node before the old first previous is this particular node. We use some n because we have to wrap it in an optional type. So the old first points to this newly created node. We update this reference because n is the first node now. We update the list reference to some n, and then we return n. Okay, so that's the function. And what does it do? It takes a doubly linked list. It takes a value. It inserts a new node which has the value as its contents at the first position and returns you the same node. Okay, so that's what insert first does. Okay, so now let's look at another function, insert after. So what does insert after do? Insert after takes a node to insert after, takes a value, right, to insert in the new node. It first creates a new node called n prime, right, whose value is v, and inserts it after n, the given node n, right, and it returns the newly created node n prime. Right? So this is what it's doing. So again, just like before, we create a new node for that has the value v, right, and because we are inserting after n, the previous of the new node is going to be the node that we are inserting after. The next node is going to be the next node of n. Okay, and if the next node does not exist, then we do nothing. If the next node is some old next, then we have to update the previous pointer of the next node, old next node. So we do that here. Old dot next is previous and some n prime, right? This is the newly created node. And finally, what we do is we update the next node of the node that we are inserting after to this newly created node. We return the node. Of course, I'm sort of hand-wavingly explaining this, but you can just draw this out and this is just work out, right? If you've done doubly linked list before, which I assume you have, this is no different, right? We just use like OCaml, some OCamlisms to explain it. So that's insert after. So yeah, delete is going to be just the usual one. The only thing that we have to do in delete, as we do in C, is we have to update the previous pointer and the next pointer, right? So we have to do both of that, and that's it. It just works out. Okay. So we've defined all of these imperative features that you would find, right? So we've defined insert and remove, but we can also do functional features in it. So the thing that we like with higher order functions is we can do iterations over any data structure, right? So we define an iter function, right? Iteration function takes a list and takes a higher order function f and applies f on each value in the list from left to right. So it is just iterating. It is not returning you anything useful, but it's just going through the list and applying this f function. So because f is not returning anything useful, it is just an alpha to unit function. So we run f for effect. It might just be like print each value or something like that. So it takes a list and then this higher order function and applies it over each element. So we write a recursive function for the loop, right? Yeah, I can possibly do it not like this. So I don't want to introduce new syntax. So I can write it like this. So I'm going to call this function with whatever is the result of dereferencing t. So that can be an optional type if the list is empty. So in which case we don't do anything. If it is not empty, so we get some E1, right? Some node, and we extract the value in that node and apply the function f that we supplied. That's the higher order function that we got, and we simply loop until we reach the end of the list. Oops, unbound value L. Okay, so yeah, I'm avoiding some syntactic sugar that I had used. Anyway, so loop is a recursive function that takes a list and then iterates to the end of the doubly linked list, right? So the whole function has type, take a doubly linked list, take this higher order function, right, and apply it to each element, and it's not going to return anything useful, so it returns unit. Okay, so this is the termination case for the iteration, so which returns unit. So this whole function returns unit. Okay, so we've done iteration, but you can also imagine doing folds, right? If you implement fold over the doubly linked list, you can use that to implement iteration and whatnot. So you can do all the things that you want. But I just wanted to give you an idea of how to use these things. So let's play with this, right? So let's create a empty doubly linked list. Let's first insert a node with 0 in it. And then I'm going to insert 1 after it, right? So I insert first a node with 0 in this list, which returns the node n0, right? So that's the first node. And I'm going to insert a new node with value 1 after n0. Let me finish this. And then we insert a new node with 2, right, as the value. Okay, so we just create a doubly linked list with 0, 1, 2 as the contents. Srisha has a question. Sir, in the previous functions, why did we wrap the pattern match with begin and end? Should we always do that? Um, where do we do begin and end? Here. Oh, here. Okay. Yeah. You don't need it. You can do. You can do this if you want. The reason for doing that is if you write it like this, right? The OCaml will interpret this as something like this. By default. So when you have this is unfortunate. This is syntactic. It's a bad syntax, right? So essentially, the parser will look at the original definition as a definition like this. All of this comes under the none case, right? So that's not what we want here, right? So the semicolon is to blame. Because I use a semicolon here, it is unclear whether the semicolon ends the whole match with block or this single expression. And it always ends the closest expression. So it ends this expression, and this everything else comes under this block. And that's not the intention. So that's why we needed this begin and end. But you can also use brackets like this. So if you use a bracket like this, open close, then that will also work. Does that answer your question, Srisha? Okay. Yeah, I don't prefer brackets because begin and end are nicer to read, and it's a bit difficult to read the brackets. Okay, so let me move on. So I created a linked list with three nodes 0, 1, 2. So it prints the actual values, right? We can have a look actually. So the list itself is weakly polymorphic because this happens to be an application which creates an effect, right, and returns something that is polymorphic. But just like we saw earlier, right, this value restriction, because of value restriction, we have a weakly polymorphic doubly linked list. Initially, the doubly linked list is empty, right? So its content is none. So when you see content is none, it is a reference that points to a reference which is a box which has none in it. So it's an optional value, but it's a reference, right? So the contents is none. And then what we did is we inserted the first node in the list with content 0, right? And what you end up having is n0 is an int node, and the value is 0. Next is none, previous is none. Okay, so that's fine. And n1 is also a node, right? It is also an integer node. Its value is 1. Its next is none, right? Because that's the last node. Its previous is this node 0, right? So it says previous is sum. This whole thing is just referring to the content here, right? So previous of n0 is none. So that's the first node. So previous is none, right? The value of the first node is 0 because the value is 0, right? And we see something curious here, right? We see next equals some cycle. Why do we see this? Because next equals some, the same node that we are defining here, right? So you can sort of replace this with n1 here, right? This will be n1. But that is not what OCaml prints, because OCaml, the pretty printer tries to recursively traverse through the entire data structure until it can sort of print everything. But that's not true here, right? If you keep going on and on with this, this is an infinite loop, right? So you have a next pointer from n0 to n1 and a previous pointer from n1 to n0. So if you try to do it naively, if you just go ahead and print everything, this would print the I mean, this would not terminate, right? And just like graph traversal, what you do when you traverse graph is you sort of have visited nodes, and the current node that you're defining is happens to be visited. So here it says cycle, but you can sort of abstractly, right? This should be N1 is the idea. N1 is not defined until this value is defined. So you can't define, it's like a chicken and egg problem. So that's why the pretty printer avoids printing N1 and just print cycle, but that's the intention. And similarly, what is the last expression? That is an integer node. We don't give it a name, so we don't actually see anything here. Its value is 2. That's the last node, so next is none. And its previous is going to be N1, right? Its previous is going to be sum. This whole thing, right? This whole thing is this whole thing. And there are cycles here, but that's the reason. The reason there is a cycle is just what I had explained now. Okay, so we sort of see what is printed. Let's see if it actually works out, right? So I'm going to iterate over the list and print the values. I'm doing printf %d. I know that the values are integer. I'm introducing a new line character, and I'm also flushing the buffer for every printing. This is strictly not necessary, but I'm just using it because this JavaScript interface that we are using expects a flush in order to show the output. But otherwise, I'm just printing out the values 0 and 2. Okay, so that's doubly linked list. So we've seen references, we've seen mutable record fields, and we saw that references are in fact implemented using mutable record fields. That is the third way of introducing mutations, general purpose mutations in OCaml. Those are arrays, right? Just like you have arrays in C, arrays are useful in OCaml. So again, arrays are contiguous data structures, right? They have efficient accesses and so on. They are not linked. So there are reasons to have arrays in the language. And so since we are looking at a new primitive, we are going to look at the syntax and semantics, right? So there is going to be static semantics, the types, and the dynamic semantics, what it actually does. So syntax, right? First thing that we do for declaring arrays is we use the syntax which is similar to lists, but has this bar, right? So if I write something like this would be a list which has into 1, 2, 3. For arrays, we use this syntax. Again, just syntax, just go with the syntax. So this defines an array that has 1, 2, 3. And we have a static semantics. We have a type called array. And A is an integer array, right? And so we want to do two things, right? We want to read the elements of the array and store into a particular indices. And the syntax is here. So if you want to retrieve the ith element of an array A, you do A dot open bracket I close bracket. Right? So this is so I'm going to retrieve the first element of the array. So A dot 0. So that gives me 1. Right? And because we have type safety, right? We have type safety. We cannot, unlike C, we cannot allow you to read arbitrary indices. That would just be wrong because the memory in that location could be anything, right? I don't know what it is. And similar to, say, Java or JavaScript or any other language which enforces type safety and memory safety, whenever you access an array index, we always check the bounds, right? Hence, if you access indices which are outside of the bounds, you'll get an error. So here I'm accessing the element at index 0, but the length of the array is 3. So the maximum index that I have is 2. Right? So this will raise an exception. Right? This is not returning some arbitrary value. This actually raises an exception saying invalid argument array index out of bounds. This is quite important for type safety, right? Because yeah, there could be arbitrary things there. Integer is fine. Imagine you have an array of say trees or something, and then I can't make up trees by reading arbitrary bits. That would just be wrong. Okay, so that is array read, and you can store into array using the left arrow syntax. So here is so what I'm doing here is I'm updating the value at index 1 to 0. Okay, so so I use the syntax and I just retrieve the array here. So I updated the value at index 1 to 0, so I get 0, 1, 0, 3 instead of 1, 2, 3, which was earlier, and I can access it here, which is 0. Arrays behave very similar to arrays in C. Actually, their memory layout is also very similar, right? So I'm not going to say much about this because you programmed with arrays already in C. You should look at the array module. At this point, you know enough OCaml to sort of look at the standard library that has certain types and that has documentation. You should be able to understand what's going on. There is nothing surprising here. It works like C-like arrays. Okay, so just to conclude this lecture, so there are benefits to immutability, right? Programmer doesn't have to think about aliasing. So we don't have this notion of what physical and structural equality is. The language implementation is free to share objects, right? If I happen to have the same value, which happens to be allocated at as two different objects, and if the values are the same, then the compiler can internally choose to use a single object. And because I don't have any mutable features, I wouldn't be able to tell a difference, right? I can only use structural equality, and structural equality anyway tells that both objects are the same. So this that makes things simpler. It also, having mutability also introduces the problem of value restriction, right? So now you have to think about what weak polymorphism is and so on. It is easier to reason about what your program does. Your program has a specification which is fully defined by the type, right? But when you have mutability, the type doesn't capture what is going on. The program might have some updating a global variable which is not captured in the type. So it is not at all clear what it is doing, right? So there are benefits to immutability. And when you start doing parallel programs, right, having immutability is great because if I have something that is purely functional, I can create 7 copies of it. All of these will not interfere with each other because there is no mutation going on. But you cannot do this when you have mutable features, right? If each of them has a reference which it is internally updating, if you create 7 copies and run it in parallel, all of them are operating on the shared data structure. You will have all the problems of parallel programming, which I think you will study in operating systems later. But that said, mutability is useful, right? Just like we saw doubly linked lists, we want to use things like arrays, which have certain memory representation. We want to use hash tables. We want to use red-black trees and whatnot. So all of these have implementations in OCaml. So all of these are implemented in an imperative fashion, right? So what is the takeaway from this lecture? The idea is that use immutable data structures unless performance cannot be compromised, right? Don't go for mutable implementation. Start with an immutable one. And if you see that there is necessary for performance where you think mutations will give you better performance, then go for it. Right? This is what standard library does. Standard library has hash tables and mutable sets and so on. They're all implemented in a mutable way, but have an interface which sort of looks very functional. I think that's a reasonable compromise to go with. And that's all I had for this lecture. I'll stop here. I think I've already taken 5 more minutes. So I'll see you tomorrow. Thank you very much.